I want you to start off today by picturing something in your mind.
Okay, I'm picturing it.
Try to picture a colossal, completely pristine, just ultra-modern commercial building.
Right.
Maybe it's a sleek skyscraper in a major downtown financial district, or, maybe it's a state-of-the-art manufacturing facility building semiconductors.
Or even one of those massive data centers, right?
Yeah, exactly. An enormous data center processing millions of transactions a second.
Sure.
It's the kind of place with perfectly manicured landscaping, gleaming glass facades, and biometric security at the front door.
The ones where the smart lighting automatically adjusts to the time of day.
Right. It looks incredibly intelligent, flawlessly clean, and just completely under control from the outside.
Mm-hmm.
But if you take a service elevator all the way down, past the immaculate lobby, past the subterranean parking garage, and step into the hidden basement.
The mechanical heart of the structure.
Exactly. If you go down there, you will find a dangerous, archaic, chemical-drenched secret. And this secret is quite literally holding the entire structure's energy efficiency and the bodily safety of the people working down there completely hostage.
It truly is the ultimate operational paradox of our time.
It really is.
I mean, we have constructed these monumental buildings that look like they belong in the 22nd century, but the internal systems keeping them habitable are relying on maintenance protocols that feel like they were, ripped straight out of the Industrial Revolution.
Exactly. And that is the exact contradiction we are tackling in today's deep dive.
Right.
We are going on a mission to explore the fascinating and honestly mind-blowing intersection of industrial thermodynamics and human safety.
It's a big topic.
It's huge. We're going to unpack how replacing static, outdated HVAC systems, those enormous air conditioning and cooling units, with automated dynamic physical cleaning and smart sensors does something amazing.
Yeah, it doesn't just save staggering amounts of electricity.
No, it completely, 100%, eliminates the need for human workers to handle highly toxic, life-threatening chemicals on a routine basis.
Which is really the core of what we are looking at today.
Right.
We have a truly fascinating stack of sources to guide us through this landscape.
Yeah, tell them about the sources.
Well, on one side, we have highly technical insights from an engineering firm called GTAKE. They break down the precise mechanics of variable frequency drives, or VFDs,
Yeah.
and they look at the thermodynamic realities of cooling tower systems.
Right, the heavy hardware stuff.
Exactly. And on the other side of the spectrum, we have this intensely philosophical, almost poetic operational thesis from a team of field engineers.
I love that one.
Yeah, they focus on something they call restorative engineering.
Okay, let's unpack this right out of the gate.
Let's do it.
Because when you first hear terms like HVAC maintenance or chiller efficiency, it sounds, let's be entirely honest, a little dry.
Oh, absolutely.
I mean, it sounds like a white paper you scroll past in a trade magazine while waiting for a meeting to start.
Yeah, it doesn't scream excitement.
But as I read through these sources, I realized this is actually a thriller.
It really is.
This is a story about the unyielding physical laws of the universe, dangerous, volatile chemicals, and a fundamental shift in how we value human life in industrial spaces.
What is genuinely fascinating here are the stakes involved.
Right.
Because this isn't just about a building manager trying to shave a few percentage points off their monthly electricity bill.
Though that certainly happens as a byproduct.
Yeah, of course it does.
Yeah.
But if we connect this to the bigger picture, this is about absorbing industrial risk.
Yes.
It's about acknowledging that forcing humans to face hazardous conditions just to keep a building artificially cool is a profound architectural and engineering failure.
So let's start at the very foundation of this problem, down in that metaphorical, dimly lit basement.
The chillers.
Right. Let's talk about what the sources define as the insulation trap.
Right, because to understand the brilliant solution, you have to intimately understand the enemy.
Exactly. And the enemy here is shockingly mundane.
Right.
It is just mineral scale.
Yeah. To set the stage properly, we need to understand what a commercial chiller actually is.
Walk us through it.
Well, when we use the word chiller, people often picture the little window air conditioning unit sitting in their apartment.
Right, or like a fancy refrigerator.
Exactly. But a commercial chiller is nothing like that. It is a monolithic piece of heavy machinery, often the size of a city bus.
Wow.
And it relies on a continuous, high-volume water circulation process.
Okay.
Hot water from the building's internal systems, carrying all the heat generated by servers, machinery, and human bodies, is pumped into these chillers,
Uh-huh.
and then it flows through hundreds, sometimes thousands, of condenser tubes.
And these tubes aren't just like regular PVC piping, right?
Oh, absolutely not. These tubes are typically manufactured from high-grade copper, or occasionally titanium.
Titanium, wow.
Yeah, and the reason for that material choice comes down to atomic structure.
Right, conductive metals.
Exactly. Those specific metals have free electrons that make them exceptional thermal conductors.
Okay, so the heat moves through them easily.
Right. The heat from the building's hot water transfers instantly through the microscopic metal wall of the tube into a separate cooling medium.
Which is usually a refrigerant, right?
Usually, yes. The heat is pulled out, and the newly chilled water is sent back up into the building.
So it keeps the data center from melting down.
Or the hospital operating room perfectly cold.
Right. But here is the catch. The water flowing through those massive industrial condenser pipes isn't perfectly pure, triple distilled laboratory water.
No, it's surely not.
It is usually municipal city water or raw industrial water. And that means it carries a heavy load of dissolved minerals.
Precisely. And this is where the physical reality of the universe asserts itself against human engineering.
The minerals cause a problem.
A huge problem. As that crucial heat transfer occurs, as the temperature fluctuates across the surface of the copper, those dissolved minerals literally precipitate out of the water.
We were primarily talking about calcium carbonate and magnesium.
Yeah. And due to the unique chemistry of calcium carbonate, it actually becomes less soluble as it gets hotter.
Why, really?
Yeah. Most things dissolve better in hot water, like sugar and tea. But calcium carbonate is the opposite.
Oh, wow. So right at the hottest point, the surface of the condenser tube, the minerals just drop out of the fluid.
Exactly.
And they don't just float away harmlessly.
They do not. They cling to the internal walls of those pristine copper and titanium tubes.
I mean, that sounds bad.
It is.
Yeah.
Over time, hour by hour, month by month, they build up.
Right.
And they don't just build up as a soft, easily washable sludge. They crystallize.
They turn into rock.
Yeah, they bake onto the metal, forming a hard, calcified mineral scale, and it's often accompanied by biological fouling.
Biofilm. Basically slime.
Right, which acts like a glue holding the rock to the metal.
And this calcified rock is what the sources refer to as the insulation trap.
Exactly.
Because, I mean, if copper is a phenomenal conductor of heat, mineral rock is the exact opposite.
It's a terrible conductor.
Right. It's a phenomenal thermal insulator.
Exactly. The entire engineering purpose of the chiller is rapid heat exchange.
Yeah.
The internal compressor relies entirely on the high conductivity of the copper tube to pull the heat out of the water.
But now you have this strict thermal barrier.
Yeah, this literal layer of rock sitting directly between the water and the metal.
Let's use an analogy that really grounds this in everyday physics.
Sure.
It is essentially like trying to boil water on your stove. But instead of putting a thin copper or steel pot on the burner, you put a thick ceramic coffee mug over the flame.
Oh, that's a great way to picture it.
Right. The heat from the stove is still there. It's burning just as hot.
Yeah.
But that ceramic barrier completely blocks the thermal energy from transferring to the liquid efficiently.
Exactly. So the burner has to work exponentially harder and longer to achieve the same result.
That makes total sense. So what does the chiller's computer system do when it senses the water isn't getting cold fast enough?
It ramps up. It has to work harder.
It just brute forces it.
Right. The compressor is forced to draw immense, sometimes staggering electrical loads just to brute force the heat transfer through that barrier of mineral scale.
You know, the sources drop a statistic that honestly made me pause. I had to reread it just to be sure I saw the numbers correctly.
The energy consumption stat.
Yeah. They note that chillers can consume up to 60% of a commercial building's total electrical energy.
It's unbelievable, isn't it?
60%. So if that monolithic machine is suddenly struggling to push heat through a layer of rock, the financial and environmental drain isn't just an annoyance.
No, it's not.
It is a catastrophic operational hemorrhage.
It creates an enormous operational choke point.
Yeah.
And historically, the way the facility management industry has dealt with this specific choke point is where the true horror of the situation lies.
This is where it gets scary.
Because you simply cannot just leave the mineral scale there. If
Yeah.
you do, the chiller's compressor will eventually burn itself out from the strain.
Which means total system failure.
Right, or the skyrocketing electricity costs will just bankrupt the facility's utility budget.
Right.
So the rock has to be removed, it has to be cleaned.
And here's where we get to the traditional legacy maintenance method.
Yeah.
And frankly, considering we were talking about buildings with biometric scanners and AI-driven lighting, This sounds like a terrifyingly primitive solution.
It really does.
To clean these tubes, the facility managers have to initiate a total system shutdown.
They take the chiller entirely offline.
Yeah, and then human operators have to manually strip the scale away. And how do they do that?
By handling highly hazardous, incredibly aggressive, toxic chemicals.
They are essentially pumping raw, highly concentrated industrial acid through the building's internal systems to dissolve the rock.
Yes.
It's completely wild. I was reading this and thinking, this is exactly like treating a patient who has a clogged artery by pouring raw acid into their bloodstream while they're wide awake.
Just hoping it burns away the plaque without killing the patient.
Exactly. It's incredibly harsh. It demands absolute downtime, which a hospital ICU or a global data center absolutely cannot afford.
No, they can't.
And it is intensely dangerous for the human being holding the hose.
Which brings us to a profound philosophical concept outlined in the restorative engineering source material.
Right.
The authors of this engineering thesis describe something they call the baseline of fear.
I found this part so compelling.
It's incredibly powerful. To illustrate this, they share a lived story from their engineering past. Years ago, this particular team of engineers was observing factory workers whose daily job required them to handle active explosives.
Yes, that story was intense. Let's really dig into the psychology of that because it sets the tone for everything else.
It really frames the entire philosophical argument of the text.
Yeah.
The engineers noted that these workers handling the explosives moved in a very specific way. They described them as moving like, quote, people holding their breath. They weren't just executing a job, they were actively surviving their shift. Fear wasn't an acute, sudden reaction to an emergency alarm. Fear was their absolute baseline operating state.
Every single movement.
Exactly. Every turn of a wrench, every footstep was deeply calculated to avoid a catastrophic, fatal mistake. The adrenaline toll on the human body in that state is immense.
And engineers look at that scenario, and they look at standard HVAC maintenance, and they say, this is unacceptable.
Right. They connect that extreme, visceral example of handling explosives directly to the manual chemical maintenance of commercial chillers.
Yeah.
They argue that forcing a facility maintenance worker to suit up in heavy hazmat protective gear to handle highly toxic volatile acids.
Just a strip scale out of a metal tube.
Exactly. To risk severe, life-altering chemical burns or permanent respiratory damage just so a building can stay comfortably cool.
It's crazy.
They argue that Shimeri is treating human safety as an acceptable, routine operational hazard. It is treating the worker as a replaceable, fleshy component in a thermodynamic equation.
The source provides this stark, highly visual contrast that really stuck with me.
The split screen.
Yeah, I want you to visualize this. They ask the reader to imagine a split screen. On the left side of the screen, you have this thick, heavily calcified mineral scale, heavily coating the inside of a copper pipe.
It looks rough, porous, almost diseased.
Exactly. And on the right side of the screen, you have the exact same copper pipe, perfectly polished, gleaming, completely clean, operating at peak thermal efficiency.
Right.
The buildup on the left happens constantly. It happens silently in the dark. You don't see it until the electricity bill spikes by tens of thousands of dollars, or the server room temperature alarm goes off.
Yeah.
And the only bridge between the decaying image on the left and the pristine image on the right has traditionally been a vulnerable human being holding a plastic bucket of toxic chemicals.
Which raises a vitally important question, one the authors force us to confront.
Why have we accepted this?
Exactly. Why is this hazardous chemical intervention the industry standard?
Yeah. Why?
The authors argue that it is because we have historically viewed industrial risk and human injury as something to simply be managed.
Like perhaps mitigated with better gloves or better training manuals?
Right, rather than something to be engineered out of existence entirely.
Okay, so if chemical intervention is so profoundly dangerous, so thermodynamically inefficient, and requires shutting down critical infrastructure.
There has to be a better way.
Right. There must be a way to solve the problem at a fundamental physical level before the scale even gets a chance to form. Like, if we know the chemistry of why the rock forms, why are we letting it bake onto the tubes in the first place?
That exact leap in logic, that refusal to accept the status quo, is what leads to the first principle of physical interference outlined in the text.
I love this part.
The engineering mandate becomes incredibly simple. Prevent the scale from ever forming.
Right.
Do not wait and react to it once it's a massive problem causing a 60% energy drain. proactively eliminate the physical conditions that allow it to exist.
Enter the automatic tube cleaning system, or ATCS.
Yes.
When I first read about how this actually works, I actually laughed out loud.
Because it's so low tech?
Yes. It is so beautifully, elegantly simple compared to the toxic chemical nightmare we just spent 10 minutes talking about.
It truly is the ultimate embodiment of bridging simple physical mechanics with smart industrial automation.
So let me describe this for you because it's brilliant. Go for it. Instead of waiting for the mineral scale to build up over 6 months and then shutting the whole data center's cooling system down to pour acid into the pipes, the ATCS constantly circulates these small, soft, orange neoprene sponge balls through the titanium or copper condenser tubes.
Orange sponge balls.
Yes.
And the crucial engineering detail here is that these spheres are slightly oversized compared to the precise diameter of the tubes.
Right. So they don't just float freely through the center of the water column doing nothing.
No, they have to squeeze.
They have to actively squeeze through the metal piping. And as they squeeze through, pushed by the immense natural water pressure of the system's own pumps, they act as physical squeegees.
It's so smart.
They physically wipe away all the microscopic mineral deposits, the calcium carbonate, the biological biofilm, before it ever gets a chance to bake on and crystallize into that hard rock.
But wait, I can hear the skepticism forming, and it is a valid engineering concern.
Yes, because my immediate pushback when I read this was, wait a second, you are intentionally pumping thousands of sponge balls through a high-pressure, mission-critical industrial pipe.
Sounds like a recipe for disaster.
Right. Doesn't that just create a colossal clogging hazard? How do these sponges not just disintegrate under the pressure, turn into sludge, and completely ruin the water supply or break the chiller?
It is the most common objection, and the sources address the mechanics beautiful.
Okay, lay it on me.
First, the material. This isn't the sponge you use to wash your dishes.
Right, it's not a kitchen sponge.
No, this is highly durable, specialized neoprene. It's designed to withstand continuous industrial friction and high water pressure without losing structural integrity or shedding particles.
Okay, that makes sense.
Plus, they are engineered for exact specific gravity, so they flow perfectly with the water current.
Okay, so they don't break apart, but how do you not just lose them in the miles of building piping? How does the system corral them?
That brings us to the critical operational detail, the closed-loop design.
Okay.
This isn't a manual process where someone dumps a bucket of galls into a tank. It is an automated, completely closed-loop cycle. There is a highly specialized catching mechanism called a ball trap.
A ball trap.
Yeah, and it's installed directly at the discharge end of the condenser.
Okay, walk me through that cycle.
So, the balls are injected into the water flow at the inlet of the chiller. They squeeze through the hundreds of condenser tubes doing their physical cleaning work.
Wiping away the scale.
Exactly. The moment they exit the tubes at the other end, they immediately hit this mechanical trap.
And what does the trap do?
The trap has a specialized screen that allows the water to pass through unimpeded. So the building gets its chilled water without any flow restriction. But it catches the oversized neoprene balls. The balls are corralled, held in a collector, and then automatically prepped for the next cycle.
And how often does this cycle happen?
Every 30 minutes.
Every 30 minutes.
Yeah.
So it is a state of constant, gentle, physical friction. It never stops.
Never.
The scale literally cannot form because the microscopic foundation is being wiped clean twice an hour.
Exactly. By deploying an automated physical cleaning system like this, the engineering team has achieved something profound.
Yeah.
They haven't just improved the thermodynamic efficiency of the chiller, though they have done that remarkably well by keeping the tubes perpetually clean.
Right.
They have engineered the chemical hazard completely out of existence. The need for acid vanishes.
It's so brilliant. And the sources go deep into the philosophy behind this specific kind of invention.
The quiet architect philosophy.
Yes. The mantra of this engineering thesis is, real technology does not replace people. It restores them.
That is a staggering departure from how we usually talk about technology today, especially in the context of corporate automation.
It really is. Usually when we hear the words automation or robotics or AI, the immediate inherent assumption is that a human being is losing their livelihood.
Right. The goal is usually to replace human labor with cheaper, faster, uncomplaining machine labor.
Exactly. But this engineering team takes a totally different, almost radical stance. They call their approach restorative engineering.
If we look closely at their thesis, their ultimate goal wasn't just corporate efficiency. Their goal was to build machines to give operators their bodily safety back.
Right.
They specifically acknowledge in the text that the financial savings from having a clean chiller saving 60% on an energy bill matter immensely to the board of directors.
Of course.
But, as the field engineers noted, the text message home to the family at the end of a shift that simply says, "I reached home safe tonight," matters more.
I want you to imagine you are that facility manager.
Mhm.
You are running a massive hospital complex or a server farm that holds critical global banking information.
Yeah, high-stakes environment.
Very high stakes. And you have a team of dedicated maintenance workers you are personally responsible for.
Right.
What does it feel like to take a pen and cross toxic chemical handling off your team's operational to-do list permanently?
It's huge.
To know with absolute certainty that you never have to send someone into a hazmat situation, risking chemical burns or worse, just to clean a copper pipe again.
It fundamentally transforms the entire culture of the workplace.
Totally.
It completely removes that exhausting, adrenaline-draining baseline of fear we discussed earlier.
Yeah.
And what's fascinating here is how this concept of quiet impact directly challenges the modern tech world's absolute obsession with loud digital disruption.
Yes. The source explicitly says, we ignore digital disruption. We build for quiet impact. An almost rebellious manifesto.
It truly is. In a world where the focus, the venture capital, and the media attention are constantly on flashy software, on generative AI, on virtual reality overlays,
Right.
here is a team of mechanical engineers saying that a brilliant line of code means absolutely nothing without a resilient physical product behind it.
Oh, that's a great way to put it.
The real, tangible, life-saving impact on human lives is happening by combining incredibly simple physical mechanics, literally orange rubber sponge balls, with basic digital automation to eliminate a fatal risk.
Yeah.
It's not loud, it doesn't make the front page of tech blogs or get discussed on cable news, but it fundamentally, permanently changes the reality of the human beings working in that dark basement.
It is the ultimate marriage of the digital and the physical realms.
It really is.
You have the software logic telling the system exactly when to release the balls, meticulously managing the 30-minute intervals, monitoring the flow rates.
Right.
And then you have the physical friction of the neoprene actually doing the dirty work that a human used to have to do with acid.
And the net result is twofold. The chiller operates at peak thermodynamic efficiency permanently, saving vast sums of money.
Right.
And the human operator is restored to a position of safety and dignity, overseeing an intelligent system rather than risking their life to manually clean a decaying one.
Okay, so that thoroughly handles the water side of the system.
The basement is sorted.
Yes. The chiller tubes down in the basement are now clean, safe, and mineral scaling is a nightmare of the past.
But this deep dive isn't over.
No, we have more to cover.
Because to understand the whole picture, we have to pivot. And by pivot, I mean we have to follow the heat.
Follow the heat, right.
Solving the problem in the basement actually reveals a colossal bottleneck elsewhere. We have to go from the basement all the way up to the roof.
To the cooling towers?
Exactly. Because up on the roof of that pristine commercial building, a totally different but equally massive physical problem is happening. Yes. To understand the complete picture of how a commercial building actually rejects heat, you need to understand the thermodynamic relationship between the chiller in the basement and the cooling tower on the roof.
Right, they're connected.
The chiller successfully removes the heat from the building's internal air, transferring it into the condenser water. We established that.
Yeah.
But thermodynamics tells us that heat doesn't just disappear. Energy cannot be destroyed. It has to go somewhere.
It has to be released.
So that newly heated water, carrying all the thermal energy of the entire building, is pumped through enormous pipes all the way up to the cooling towers on the roof to be released into the atmosphere.
And what exactly happens inside a cooling tower? For those of us who just look up and see these big industrial metal boxes steaming on top of city buildings, what is the actual mechanism inside?
Well, a cooling tower is essentially a massive, highly engineered evaporative cooler.
Okay.
The hot water arriving from the chiller's condenser is sprayed downwards over layers of heat exchange materials, which engineers call fill. Yeah. This fill is designed to break the water into thousands of tiny droplets, exponentially increasing the surface area of the water exposed to the air.
Oh, to help it evaporate.
Exactly. At the exact same time, massive, heavy steel fans at the top of the tower draw ambient outside air and pull it forcefully up through the falling water droplets.
So it's violently mixing the hot water with the outside air.
Correct. And this is where we need to briefly touch on the physics of heat transfer, because it's crucial to understanding the problem we're about to face.
Lay the physics on me.
The heat from the water dissipates into the air through two distinct thermodynamic mechanisms. The first is sensible heat transfer.
Break down sensible heat for me.
Sensible heat is the heat you can physically sense or measure with a thermometer.
Like hot coffee?
Right. If you put a hot cup of coffee on a cold table, the air around the coffee gets warmer and the coffee gets cooler. That is sensible heat transfer. But in a cooling tower, sensible heat only accounts for a small fraction of the cooling. The heavy lifting is done by the second mechanism, latent heat transfer, which is evaporation.
Phase change.
Exactly. When liquid water changes phase into water vapor, when it evaporates, it absorbs an absolutely monumental amount of thermal energy from its surroundings.
Give me some numbers on that.
To give you some math on this, it takes just 1 BTU of energy to raise the temperature of a pound of water by 1 degree Fahrenheit. That's sensible heat.
Okay, 1 BTU.
But it takes roughly 1,000 BTUs to evaporate that same pound of water.
Oh, wow, that's a huge difference.
Evaporation is a thermodynamic powerhouse. So a small portion of the water in the tower evaporates, pulling an immense amount of heat away in the process.
And then what happens to the rest of the water?
The now cooled water collects in a large basin at the bottom of the tower and is sent back down into the basement chiller to repeat the endless cycle.
It is essentially the exact same biological mechanism the human body uses to cool itself by sweating. It's not the sweat sitting on your skin that cools you. It's the phase change, the evaporation of that sweat into the air that pulls the heat away from your body.
That is exactly right. But here is where we hit the second massive bottleneck in industrial HVAC design.
Okay.
The engineering sources define this problem with a fantastic term, psychrometric ignorance.
Okay, psychrometric ignorance. I joked in my notes that this sounds like a great name for a punk rock band.
It really does.
But what does it actually mean in a strict engineering context?
Psychrometrics is the highly specialized field of engineering concerned with the physical and thermodynamic properties of gas-vapor mixtures.
Gas-vapor mixtures.
Yeah, in our specific case, the mixture of atmospheric air and water vapor, which we commonly call humidity.
Okay.
The problem lies with legacy building management system controls, or BMS. Historically, these central computer systems operate on very rigid, deeply static logic.
Static logic meaning they do not adapt to changing conditions. They just follow a simple, hard-coded script, regardless of reality.
Right. They are programmed with a fixed, unyielding temperature target.
Give me an example.
For example, the facility manager programs the system and says, return the water from the roof to the chiller in the basement at exactly 75 degrees Fahrenheit at all times.
Okay, 75 degrees.
To achieve this, the legacy system looks at the water temperature, sees it's too hot, and commands the cooling tower fans to run at their maximum possible capacity.
100% speed.
Exactly, 100% speed, desperately trying to hit that fixed number.
But the atmosphere outside the building isn't a static, controlled laboratory environment. The weather changes every single minute.
And that is the fatal flaw of psychrometric ignorance.
Right.
Ambient atmospheric humidity imposes a strict, unbreakable physical boundary on exactly how much cooling can occur through evaporation.
And what is that boundary called?
This boundary is known in thermodynamics as the wet bulb temperature.
Here's where it gets really interesting, and I want to spend some time here. Yeah. Break down the wet bulb temperature for us, because this feels like the absolute linchpin to the whole airside problem. And I think a lot of people have heard this term recently in the news regarding extreme weather, but don't fully grasp the physics.
Let's go back to your sweating analogy, because it is the most relatable way to understand this.
Okay, let's hear it.
If you are outside on a hot, perfectly dry day in the Arizona desert, you sweat. Your sweat evaporates instantly into the dry air, and you feel surprisingly cool.
Right, because the air is dry.
Exactly. The air is dry, meaning it has plenty of capacity to absorb the moisture from your skin.
Right, the classic, it's a dry heat saying. Exactly.
But if you take that same human body and put it in Florida or Southeast Asia during monsoon season, and it's the exact same air temperature, but with 95% relative humidity, what happens?
You sweat profusely.
Yes. Your clothes are soaked, but the sweat does not evaporate. It just rolls off you.
You stay dangerously hot.
Why? Because the ambient air is already completely saturated with water vapor. It is essentially full.
It can't take any more water.
Right. It cannot physically absorb any more moisture from your skin.
So the mechanism of evaporation literally stalls out and fails.
Precisely. The wet bulb temperature is a highly specific measurement that accounts for both the actual air temperature, the dry bulb, and the humidity.
Okay.
It represents the absolute lowest possible temperature to which water can be cooled through evaporation in those specific immediate atmospheric conditions.
The lowest possible temperature?
Yes. You cannot cool water below the ambient wet bulb temperature, no matter how hard you blow air on it, no matter how much you try. It is a hard limit imposed by the unbreakable laws of physics.
So connecting this crucial physics lesson back to the psychrometric ignorance of the legacy building system.
Right.
If the BMS computer is demanding that the water be cooled to 75 degrees, but because it's a super humid August afternoon, the wet bulb temperature outside is sitting at 78 degrees. What exactly happens mechanically?
The building enters a state of unwinnable conflict.
An unwinnable war.
The static software script doesn't know about the wet bulb limit, doesn't understand humidity.
It just wants 75 degrees.
Exactly. It only knows that the water is 78 degrees, and its hard-coded target is 75. So it sends a relentless command to the massive steel cooling tower fan on the roof.
Spin faster.
Spin faster. Spin at 100% maximum velocity. Do not stop until we hit 75.
But it is physically impossible to reach 75 degrees. The air won't accept the evaporation.
Exactly. The fan spins at maximum velocity, drawing staggering electrical loads, aggressively and violently churning the humid air.
Fighting a completely unwinnable battle against atmospheric reality.
The water will never, ever reach 75 degrees because the ambient humidity explicitly forbids it. But the legacy system ignores the laws of psychrometrics.
Resulting in extreme, catastrophic, and completely wasteful energy consumption.
Exactly.
I really want to paint a cinematic picture of this for the listener, because the source material does such a phenomenal job of emphasizing the physical reality of these massive machines.
Okay.
Imagine a sweltering, incredibly humid July afternoon in a major city. Up on the roof of this sleek, modern building, you have this incredibly heavy industrial steel fan.
It's massive.
It's aggressive, it's deafeningly loud, it is spinning at maximum velocity under the baking hot sun.
Vibrating the whole structure.
Yes. It is violently pulling in air, vibrating the whole metal structure, causing immense wear and tear, and needlessly burning thousands of dollars of electricity an hour.
And why?
Because a piece of static software, a dumb script written 10 years ago by a programmer who wasn't thinking about humidity, is completely ignoring the actual weather outside. It's pure thermodynamic decay.
And it gets worse.
Wait, how can it get worse?
Because the historical mechanical methods used to try and control this airflow before modern variable technology were just as fundamentally flawed as the software.
Oh, you're talking about the dampers.
Yes.
Yeah.
The GT-Take source material details how legacy systems frequently use constant fan start-stop cycles or physical mechanical dampers to try and regulate the cooling process.
Yes. Let's talk about dampers, because I have an analogy for this that made it click for me.
I'd love to hear it.
Using a physical mechanical damper to control airflow from a massive industrial fan motor that is constantly running at 100% speed. It is like driving your car down the highway with your right foot mashed all the way down on the gas pedal.
Oh, that's good.
And using your left foot to slam on the emergency brake to control your speed.
It's an incredibly destructive, highly inefficient way to operate any piece of machinery.
It's a colossal waste of energy. The motor is screaming, working as hard as mechanically possible, drawing maximum amps.
Yeah.
And you're just putting a physical steel block or a damper in front of the airstream to choke it off and slow it down. It wastes electricity and it completely ruins the machinery.
It does.
And what about the start-stop cycling you mentioned? What does that do to the equipment?
Well, frequent on-off cycling causes severe cumulative mechanical stress. Think about the inertia of a massive steel fan blade.
It takes a lot of force to get it moving.
Exactly. Every single time you turn a heavy industrial AC motor on, there is a massive inrush surge of electrical current, sometimes 6 times the normal operating current.
Right.
And there's an immense, violent torque spike on all the mechanical components. The belts snap tight, the bearings grind, the gearboxes slam.
That's that.
Over time, that constant jarring start and stop action literally tears the machine apart from the inside out.
Okay, so let's summarize the nightmare on the roof.
Yeah.
We have static logic failing spectacularly against the physical reality of humidity.
Right.
We have systems running at 100% fighting an unwinnable war against the wet bulb temperature. And we have mechanical dampers that act like driving with the emergency brake on, destroying the equipment.
It's a mess.
There has to be a better way.
Yeah.
We need a dynamic system. We need somebody that can actually read the atmosphere, understand the physics of evaporation, and adapt to it rather than blindly fighting it.
This brings us directly to the technological solution for the fans, which is detailed exhaustively in the G-Take material.
The VFDs.
Yes. Variable frequency drives, commonly referred to as VFDs, equipped with real-time psychrometric sensors.
So how does a VFD actually solve psychrometric ignorance? What does it actually do to the fan motor? And I want to get into the physics here, not just the buzzwords.
A VFD controls the fan speed not by blocking the air with a damper, but by fundamentally altering the electrical power being supplied to the motor.
Okay, changing the power itself.
Exactly. To understand this, we need a tiny bit of electrical engineering. In the United States, standard alternating current, or AC power, runs from the grid at a frequency of 60 hertz.
60 hertz, got it.
The physical speed of an AC induction motor is directly tied to that electrical frequency.
Oh, interesting.
A VFD sits between the power grid and the motor. It takes that incoming 60 hertz AC power, converts it to DC power using a rectifier, and then uses an inverter to synthesize a brand new AC output.
So it makes its own wave.
Exactly, but this time it can change the frequency, say, dropping it smoothly from 60 hertz down to 45 hertz, or 30 hertz.
And what happens when the frequency drops?
When the electrical frequency drops, the motor physically slows down in perfect sync.
So instead of running the motor at a blind 100% and physically choking the air with a metal damper, you just mathematically run the motor at 50% speed.
Exactly. It uses only the exact amount of energy required to spin the fan at that specific lower speed.
That is so much smarter.
It is. And the true intelligence comes from the integration of the sensors.
The psychrometric sensors.
Right. The dynamic system monitors the temperature of the returning cooling water, but crucially, it also uses atmospheric sensors to monitor the ambient wet bulb conditions outside in real time.
It's actually looking at the weather.
Yes. It feeds this constant stream of thermodynamic data back to the VFD's microprocessor.
This is the dynamic adaptation we were looking for.
Yes. Instead of stubbornly trying to hit an impossible fixed 75-degree target, the VFD adjusts the fan speed dynamically based on what the engineering industry calls the wet bulb approach limit.
The approach limit.
The system's logic knows the physical laws. It knows that on a sweltering, humid August day, it can only realistically cool the water to, say, 3 degrees above the current wet bulb temperature.
Because that's all the humidity will allow.
Exactly. So instead of running the fan at 100% and failing miserably, it calculates the optimal reduced fan speed to hit that realistic physical limit, and it stops there.
It refuses to waste energy fighting the impossible.
Exactly.
Let's talk about the energy savings here, because earlier you mentioned the math behind it, and I want to make sure I understand it. You mentioned the affinity laws in relation to fans. Walk me through that math.
The energy savings from a VFD on a centrifugal fan are governed by the physical laws of fluid dynamics, specifically the affinity laws.
Okay.
The crucial law to remember is this. A fan's power consumption is directly proportional to the cube of its rotational speed.
Wait, the cube of the speed. Walk me through that math so I can visualize the impact.
Let's do the math. If you need 100% airflow, you run the fan at 100% speed, and it uses 100% of its power capacity. Makes sense.
But let's say the weather cools down, or the VFD senses the wet bulb limit, and it determines you only need 80% airflow.
Okay.
It drops the motor speed to 80% or 0.8. To find the power consumption, you cube that number. You multiply 0.8 times 0.8 times 0.8.
And what's that equal?
The result is roughly 0.512.
So 51%.
Yes. By dropping the fan speed by just 20%, you drop the electrical power consumption by nearly 50%.
Wow.
It is a cubic exponential curve of savings. If you drop the speed to 50%, 0.5 cubed is 0.125.
Oh, goodness.
You are using only 12.5% of the power to get 50% of the airflow. That cubic relationship is the absolute secret to the monumental ROI of variable frequency drives.
That math is genuinely staggering. So when the internal cooling demand rises, or the outside air is exceptionally dry and favorable for evaporation, the fan smoothly accelerates to enhance heat dissipation.
Right.
But when the demand drops, or when the suffocating humidity makes further cooling physically impossible, the fan automatically mathematically slows down. It saves exponential amounts of energy.
And it prevents the system from fighting an unwinnable psychrometric war.
And this requires absolutely zero manual intervention from a human operator. It is a fully autonomous, closed-loop control system.
I love the sheer elegance of the engineering here.
Yeah.
It is so deeply satisfying to think about.
It really is beautiful.
Instead of fighting nature, instead of trying to brute force a physical impossibility with a massive screaming electric motor.
The machine actually works with the physical limits of the atmosphere.
Yes, it senses the air, it understands the humidity, and it adapts its behavior. It's like the building finally learned how to breathe properly.
It acts as an autonomous nervous system reacting to the environment in real time.
That is a perfect analogy. It is localized physical intelligence.
And the benefits extend far beyond just energy efficiency and lower utility bills. There are profound long-term mechanical benefits to implementing VFDs.
Oh, because it's not slamming on and off.
Exactly. Remember the severe physical damage caused by the frequent on-off cycling we talked about earlier? The massive torque spikes tearing up the belts and bearings?
Right, the violent shudder every time a giant fan kicks on.
VFDs completely eliminate that destructive force through a process called soft starting and stopping.
Soft starting.
Because the VFD controls the frequency, instead of slamming the motor with full 60 hertz power instantly, the VFD starts at 0 hertz.
Oh, and just ramps it up.
Exactly. It gradually, smoothly ramps up the frequency over several seconds or minutes.
It's gentle.
Very gentle. The massive steel fan blade starts turning slowly, smoothly accelerating to the required speed without any mechanical jerking.
Which saves the hardware.
This drastically reduces the mechanical shock to the entire system. It dramatically extends the lifespan of the costly motors, the bearings, the structural gear components.
And it must be quieter, too.
It even significantly lowers the noise pollution levels for the surrounding city area.
So let me get this straight. You're saving staggering amounts of electricity through cubic math. You're saving the physical machinery from literally destroying itself.
Yep.
And you're operating in perfect dynamic harmony with atmospheric physics.
Over time, as the GTAKE source material explicitly points out, these combined benefits translate into significantly lower operating costs, vastly reduced maintenance schedules, and massively improved overall system reliability.
Okay, so we've thoroughly covered the two highly technical halves of this deep dive.
The basement and the roof.
Right. Down in the hidden basement, we have the automatic tube cleaning system, the ATCS, continuously circulating slightly oversized orange neoprene sponge balls to wipe away precipitating mineral scale.
Right.
This completely eliminates the insulation trap, restoring perfect thermal conductivity. And crucially, it entirely eliminates the need for human maintenance workers to handle dangerous, life-threatening acid.
Solving the human chemical hazard.
Yes. Then, up on the roof, we have variable frequency drives, VFDs, constantly reading the atmospheric wet bulb temperature and dynamically adjusting fan speeds based on the affinity laws to eliminate psychrometric ignorance.
And solving the thermodynamic waste.
Exactly. But here is the ultimate, cynical, real-world question that always pops up in engineering.
Let's hear it.
This all sounds amazing on paper. It sounds like a perfect utopia of physics and safety.
Okay.
But this hardware, the psychrometric sensors, the high-capacity VFDs, the custom ball traps, the extensive piping modifications, none of this is free.
No, it certainly isn't.
In fact, it requires a substantial, sometimes intimidating capital investment up front.
Oh, absolutely.
So how does a facility manager or a head of field engineering actually get the corporate executive, the board of directors who only look at spreadsheets, to pay for this extensive system upgrade?
How do you sell it to them?
Right. How do you sell human safety to people focused on quarterly profits?
This brings us to phase 2 of the Restorative Engineering Manifesto, which is perhaps the most fascinating psychological aspect of this entire topic, the monetizable mechanism and the capture strategy.
The capture strategy. I love that phrasing. It sounds like the title of a corporate espionage thriller.
In a very real way, it is a form of benevolent corporate espionage, deployed for a noble, life-saving cause.
Okay, I'm hooked. How does it work?
The engineering team defines their complete integrated system as an autonomous thermodynamic restoration protocol.
Fancy words.
Very fancy. You combine the dynamic VFDs on the cooling tower fans with the physical ATCS hardware on the basement chillers. But how do you get it funded by a skeptical board?
Right. How?
You have to deeply understand the financial incentives of the people holding the purse strings.
You have to speak the language of the executives.
Exactly. The engineers in the source text call this navigating the deception filter.
The deception filter.
Yes. The board of directors generally does not want to authorize a multi-million-dollar capital expenditure solely to make the maintenance staff's lives slightly more comfortable or theoretically safer.
That is the harsh, pragmatic reality of corporate finance.
However, they will authorize that exact same massive project instantly if it guarantees a staggering, verifiable reduction in the building's total energy consumption.
They want the financial return on investment, the ROI.
Precisely.
Because, as we established, up to 60% of the building's total energy is going to these chillers and fans.
Right.
If an engineer can walk into a boardroom and prove mathematically that they can slash that massive utility number, the executive's eyes light up.
Precisely. And this is where the engineers deploy their data. They show the board the math on the VFDs governed by the affinity laws.
The cubic math.
Right, showing how dropping fan speed by 20% cuts the fan's power bill in half.
Right.
Then they add that massive financial savings on the roof to the equally massive energy savings in the basement.
Because the chiller isn't fighting a rock-hard layer of mineral scale anymore.
Exactly. The automated sponge balls are keeping the thermal transfer perfectly clean. The combined energy reduction across the entire HVAC infrastructure is staggering.
So it pays for itself.
It pays for itself remarkably fast.
You know, if you are listening to this right now and you work in a large corporate office building, you know, the kind of office where the AC seems to freeze you out at 9 a.m., but leaves you sweating uncomfortably by 3 p.m.,
We've all been in those buildings.
what you are likely experiencing is the failure of these legacy static systems. The building is blindly fighting the weather outside, burning money, and you are caught in the crossfire of the fluctuating temperatures.
That's a great real-world connection.
So bringing it back to the engineers presenting to the board, what does this all mean for the execution of the capture strategy?
It means the engineering team essentially uses the promise of massive corporate energy savings to quietly pay for human safety.
That is so subversive.
It is. They frame this entire integration to the board of directors exclusively as absolute thermodynamic compliance and high ROI efficiency.
And the board buys it.
The board eagerly signs the check because they want the financial return and the green energy PR. But the true victory for the engineers, the hidden moral victory, is that by installing this automated system to save electricity, they permanently, quietly eliminate the chemical exposure risks for their maintenance staff.
They literally smuggle life-saving occupational safety into the facility by dressing it up in a suit and tie as a high ROI energy upgrade. It is absolutely brilliant.
The text describes this as absorbing the hazard by restoring system efficiency. It is a masterful alignment of disparate incentives.
Everyone wins.
The executives get their lower operational overhead costs, the shareholders get their margins, and the maintenance workers get to go home safe to their families without handling toxic acid. Everyone wins, but the primary goal, human safety, was achieved through the Trojan horse of thermodynamic efficiency.
And the sources mention that these intelligent VFD-based systems can even integrate much deeper into the building's infrastructure. They connect with the central building automation systems, the BAS or programmable logic controllers.
Right. It's not just one isolated chiller in a basement or one isolated fan on a roof acting alone anymore.
It's all connected.
Once you digitize the control, you can have multiple chillers and an entire battery of cooling towers operating in a highly coordinated algorithmic dance.
Wow.
The intelligent control strategies can distribute the thermal load evenly across all the equipment, reducing peak power demand.
Why is peak demand so important?
Well, reducing peak demand is critical because commercial buildings are often charged exorbitant fees by utility companies based on their highest moment of power consumption.
Oh, interesting.
This deep integration supports the entire modern trend towards smart, autonomous infrastructure that reacts holistically to its environment.
Think about where this matters the most. The sources list typical application scenarios. Massive commercial skyscrapers, intricate industrial manufacturing facilities like pharmaceutical plants.
Hyperscale data centers?
Yes. Hyperscale data centers and critical care hospitals. These are places where the thermal cooling demand fluctuates constantly throughout the day and where system downtime is absolutely, unequivocally not an option.
You cannot turn them off.
You cannot just turn off the air conditioning in an active server farm running global finance or in a sterile hospital operating room just to manually clean the pipes with chemicals.
Which is exactly why VFDs and ATCS are rapidly transitioning across the industry from being viewed as optional luxury upgrades for green buildings to becoming standard, absolute baseline operational requirements for any serious modern facility.
Right.
You cannot claim to run a modern operation if you are using 19th century maintenance hazards.
It is such a deeply satisfying conclusion to this topic. You start with this hidden, terrifying, chemical-drenched hazard lurking in the dark, and through the application of precise physics, fluid dynamics, and incredibly smart, quiet engineering, you completely dissolve the problem. You engineer the danger out of existence.
It's really inspiring.
So let's comprehensively recap this journey we've been on today.
Let's do it.
You, the listener, started by picturing that flawless, pristine building. We took you down into the hidden basement and showed you how microscopic mineral scale silently builds into a rock-hard thermal insulator, unnecessarily draining up to 60% of a building's energy, and, far worse, trapping dedicated maintenance workers in a physiological baseline of fear as they were forced to handle highly toxic cleaning acids.
Terrible situation.
We explored the mechanical elegance of the automatic tube cleaning system. Something as profoundly simple as automated, slightly oversized neoprene sponge balls can provide the continuous physical friction needed to eliminate that chemical hazard entirely, proving that the simplest physical solution is often superior.
Simple but effective.
We then followed the heat up to the roof, exposing the psychometric ignorance of legacy computer systems that blindly force massive steel fans to fight unwinnable battles against atmospheric humidity. And we saw how variable frequency drives, armed with real-time wet bulb sensors and governed by the cubic math of the affinity laws, act as an autonomous nervous system.
Right.
They respect the physical limits of the atmosphere, smoothly saving the heavy machinery from tearing itself apart while drastically cutting immense energy costs.
And we wrap it up with a strategy to actually get it done.
And finally, we unpacked the brilliant capture strategy, how clever field engineers use the massive financial ROI of these thermodynamic efficiencies to quietly, subversively fund the permanent removal of occupational hazards from their teams.
If there is one overarching thesis to pull from all of this highly technical information, it brings us squarely back to the ethos of the quiet architect.
I love that phrase.
The fundamental belief that true technology must restore human safety and human capability, not just increase profit margins. We should build for quiet impact.
Absolutely.
It is a powerful, profound reminder that the absolute best, most advanced technology in the world doesn't just make machines run faster or cheaper. It actively, tangibly protects the vulnerable human beings who are tasked with operating them. It bridges brilliant physical mechanics with smart digital logic to completely absorb the risk on behalf of the worker.
I think that is the perfect, poignant note to land on. But before we wrap up, I want to leave you, the listener, with a final provocative thought. Something to really mull over when you go back to your own work tomorrow, whatever industry or field you happen to be in.
Leave them with something to think about.
If a team of HVAC engineers can completely absorb the fatal risk in massive industrial chillers using something as remarkably simple as physical friction and smart atmospheric sensors, look closely around your own daily reality.
What's your chemical trap?
What other hidden, dangerous, or simply soul-crushing tasks are we forcing humans to do every single day simply because that is how it has always been done? What is the exact equivalent of the toxic chemical cleaning trap in your world, in your office, in your software, or on your factory floor?
And more importantly,
using the philosophy of the quiet architect. How can you use your skills to engineer it completely out of existence?
that's the real question.
Think about that pristine building we started with. Think about what was hiding in its basement. And think about how you can start circulating your own automated sponge balls to clean up the hazards in your own life.
Well said.
Thank you so much for joining us on this deep dive into the hidden world of restorative engineering. We'll see you next time.